Imagine giving a model a single sentence in Arabic, Japanese, or German and having it tell you the exact language instantly. No spaces, no dictionary. Today, we were building a multi head attention language detector from scratch, line by line, layer by layer, so you actually understand why every piece is there, not just copy code. I'm Surf, let's get started. Quick setup first. In Colab, go to runtime, change runtime type, select T for GPU and save. That give us a free GPU power so training runs fast. Let's confirm it's active with 2 lines. Let's bring in our tools, NumPy for numerical work and Pickle so we can save our finished project later. From TensorFlow, we bring in the model class and the actual building blocks, embeddings, multi-head attention, layer normalization. Hence, tokenizer will split our text into character and pad underscore sequence will make every sentence the same length. Label encoder turns our language name into numbers since a model can only ever work with numbers, never raw text. And the dataset library pulls in our real data from Hugging Face. Now let's load our data. We were using a real dataset from Hugging Face called Papuka Language Identification, 70,000 training sentences and 10,000 validation sentences across 20 different languages. A bigger, more varied dataset means the model learns real patterns instead of just memorizing. Right now, our languages are labeled with short tags, EN for English, JA for Japanese. A neural network cannot train on text tags directly. Its neat numbers label encoder maps every language tag to a number 0 through 19. Since we have 20 languages total, we will convert back to a readable name only at the end when we show a real prediction. Let's slow down here because this decision matters a lot and most tutorials keep explaining it. Normally in NLP, text is split by spaces into words. That works fine for English, but Japanese and Chinese don't use space between words at all. Word splitting would completely breaks on them, treating a whole sentence as one giant unrecognizable word. So instead, we set character level equal to true, we split by individual letters and symbols instead of whole words. Every language is made up of character, spaces are not, so this works everywhere. Notice vocabulary size equal to 300, tiny compared to a word level vocabulary which could be 50,000 plus. That's because there are only a few hundred unique characters across all 20 languages combined. Smaller vocabulary and it still works for every language, and paradoxical sequence make sure every sentence is standardized to 200 characters long. Now the heart of this project, the architecture. Think of it like building with Lego blocks, one piece at a time, because each layer has exactly one job. The input layer set the expected shape. Every sentence padded or trimmed to exactly 200 characters. The embedding layer then turns each character ID into a list of 128 numbers instead of just one. Right now, a character is just a number, and numbers like 12 and 5 don't mean anything relative to each other on their own. Embedding gives each character its own 128 number profile, and these numbers are learned during training. So, characters that behave similar across languages end up with similar profiles. Now the core feature, multi-head attention. For every character in the sentence, this layer asks which other character here should I pay attention to. To understand this one, some character matters together a lot, recurring patterns typically of a language, others don't matter much at all. Number of heads equal to 4 means it does this 4 times in parallel, each head free to notice a different kind of patterns. One might focus on letter pairs, another on words ending. Then look at X plus attention's output. That's the residual connection. We add a original character data back in. So even if attention misses something useful, the original information isn't lost. Layer normalization right after keeps all these values in a stable, consistent range so training doesn't become unstable. We still have 200 separate character vector right now, but we want one single answer for the whole sentences. Global average pooling averages all 200 down into one summary vector, the sentences meaning fingerprint. A dense layer refines that summary further, and the final dense layer with softmax turn into 20 probabilities, one per language, all adding up to 100%. Whichever is highest is our prediction. Let's try. Thanks to the T4 GPU, Training across 70,000 sentences takes just seconds per epoch. If this is helping, a subscribe, keep this deep dive builds coming. Now let's watch it train. After just 4 epochs, this model reached about 96% accuracy on sentences it had never seen during training. That's a strong, trustworthy result backed by the tens of thousands of real examples. Numbers on paper aren't enough. I want a real proof. I wrote my own self introduction, translated it into all 20 languages by hand, and tested the model on sentences it had truly never seen in any form. Watch Arabic correct, Bulgarian correct. This is the model actually understanding character patterns per language, not memorizing training data. Last step, we save the trained model, tokenizer, and label encoder so we can reuse this exact model anything without retraining. And that's the full build from raw text to character level tokenization to a real transformer style attention model to your working 20 language detector. If you followed this step by step, you now understand exactly why every layer is there, not just what it is called. If you want more builds like this, subscribe. See you in the next video.